Now next set of 5 problems, they are integer type questions. Now let us look at the first problem. An infinitely long solid cylinder of radius r has a uniform volume charge density ρ. It has a spherical cavity of radius r by 2 with its center on the axis of the cylinder, as shown in the figure. The magnitude of the electric field at a point P, which is at a distance 2r from the axis of the cylinder, is given by the expression 23 rho r divided by 16k epsilon naught. The value of k has to be found out. Now since it's a integer type question, so we have the option of 0 to 9. Okay, now this problem is to be attempted applying Gauss Theorem at these 2 points at point P, considering 2 different cases. In first case, we will assume that there is no cavity inside the cylinder, and then we'll find out electric field at point P only due to the complete cylinder. Okay, or we can call it as E1. And the other case in which we will find out the electric field at point P due to the presence of charge in this portion. If cavity is filled with this much of charge, then there is no cylinder present, then only due to the charge present in this sphere we have to find out its electric field at this point, which is E sphere. That, let us say, we call it as E2. Now at point P, the electric field due to this cylinder with a cavity will be E1 minus E2, because in E1 the charge which is actually not there in the cavity is also being considered, and to take care of it we have found out electric field due to that portion of sphere, and then we are subtracting E1 minus E2. Now this problem becomes very simple. So in the case of infinitely long cylindrical wire at a point P, which is at a distance of 2r from the center, if we apply Gauss theorem, flux is given by E dot ds, which will be equal to q by epsilon naught. Now let us say we take this cylindrical portion only. We are not taking the entire infinitely long cylinder of, let us say, length L. So we have to consider a cylindrical surface, a Gaussian cylindrical surface passing through point P of radius 2r, and the electric field will be leaving normally from the surface of this Gaussian surface. So by symmetry we know that the value of E will be same, so we can take E as constant, which will come out. Okay, and integral of ds can be written as total surface area, which is 2 pi times 2r into length L. Okay, so 4 pi RL is the total surface area times electric field is the flux. Now we have to find out charge which is enclosed in this portion, okay, in this cylinder. Now charge enclosed will be equal to volumetric density is rho, total volume is pi r square into length L divided by epsilon naught. Now this flux is equal to this value, okay, charge enclosed upon epsilon naught. So pi will cancel out, r will cancel out like this, L will cancel out, and we will have E is equal to rho by 4 epsilon naught. Now this is E1, or due to the infinitely long cylinder. Now let us find out electric field 2 at point P in the absence of the infinitely long cylinder, and only charge is present in this spherical portion. Now the radius of this sphere is r by 2. So if we apply Gauss theorem, and we assume a sphere of radius 2r, then electric field will be leaving normally from each point on the sphere, and it will be also leaving normally from point P, from the surface. Now phi is equal to E dot ds, that is equal to Q enclosed upon epsilon naught. E will be constant, that is E2, and total surface area will be equal to 4 pi 2r whole square. Okay, now that is equal to Q enclosed. Charge enclosed is rho times 4 by 3 pi r cube, where r cube is r by 2 cube, that is r cube by 8 upon epsilon naught. Okay, so E2 times, now this 4 into 4 is 16 pi r square is equal to 4 by 3 pi rho r cube by 8 epsilon naught. Okay, now so this pi will cancel out, so we will have 4 here, and E2, and this will cancel out this. So the value of E2 is rho r upon 4 into 8 is 32, 32 into 3 is 96 epsilon naught. Okay, so the net electric field at point P will be E is equal to E1 minus E2, where E1 is rho r by 4 epsilon naught and E2 is rho r by 96 epsilon naught. Okay, so we take rho r by 4 epsilon naught common, and we will have 1 minus 1 by 24, which is equal to 23 times rho r by 4 times 24 epsilon naught. Okay, now if you look at the problem, the expression was given to us as 23 rho r by 16 k epsilon naught. Okay, so if we compare this with 23 rho r by 16 times k epsilon naught, that means 16k becomes 24 times 4. So this is 4, and the value of k is 24 by 4, that is 6. So the correct answer is k equal to 6.